Hi, so I'm Pranav, and in this video, we will be looking at testing a 4-bit adder circuit or 4-bit adder IC using an NImyRIO. Typically, to talk about adder circuit, a full bit adder, a 1-bit full adder, the following truth table wherein, as can be seen, the input bit Cin is the carry from the previous logic level, from the previous logic stage, and there are two input bits A and B, as my cursor shows, and then there is the C out bit, which is the output of that particular bit addition, and the carry sum is carried forward to the next stage. This way, a full adder of 1 bit works, and this is the corresponding truth table for it. Similarly, for a 4-bit, there is an input bit coming from the previous stage. It goes to the first bit, then to the second bit. So this is the carry. This is the carry from the first bit to second bit. This is the corresponding outputs S0, S1, S2, and S3 are the corresponding outputs of each and every bit. And bit number 1, 2, 3, 4. That way, a full adder of 4 bits typically performs. So this is the input from the previous stage, and this is the output from this current stage to the later stage. This is the basic logic for a 4-bit binary compatibility, which will be discussed further. Similarly, for the VOL, now talking about the myRIO specifications, although it shows that it has an overvoltage protection of 16 volts, these values which we are talking here are analog input values. And if we look at the screenshot for myRIO from the datasheet of myRIO, so let me pull this really quick. This is one side of the myRIO connection, which is called as the XP connectors, and this is the other side of the myRIO, which is called as the MSP connector. So on the MSP connector, as you can see, that the voltage limitations are in the range of plus or minus 10 volts. So there can be an analog output of plus or minus 10 volts, and it can measure an analog input of plus or minus 10 volts. Although there is a provision to provide an input voltage of as high as 6 volts, uh, it is not feasible to provide such, it is not possible to measure this particular high voltages at the output levels. The primary reason for this is the this the VOL and VOH levels will be measured at the digital end, at the digital pins, and as a result of which the logic levels on the myRIO have a compatibility issue, wherein the MXP connectors, which have a nominal range of plus or minus 5 volts, lead to a limitation here. So for a VOL, for a VOH level of 5.9, since there is a limitation of 5 volts, it won't show 5.9, and there would be an error in measurement. So typically, a VOH or VOL will be determined for uh, it would be determined for uh, two VCC levels of 2 volts and 4.5 volts respectively. So this is one of the typical calculations, typical specifications of myRIO which will be in use, wherein if you can see the absolute accuracy is plus or minus 50 millivolts, whereas on the MSP connector side it is around plus or minus 200 millivolts, which is quite significant. So there is a accuracy resolution of zero point 0.2 volts basically on the MSP connector. So an approximate value compared to the VOH and VOL levels can be obtained using this particular datasheet benchmarks. So basically you have three possible tests which can be performed on the NImyRIO. Although it's a digital chip, so propagation delay is quite an interesting test to be performed. But as we can see, the sample rate for each of the cases is around 500 kilo samples per second, as we can see over here. And at a rate of 500 kilo samples per second, the propagation delay which will be measured would be quite erroneous, because propagation delay for this particular integrated circuit is in the range of 1 to 2 nanoseconds, whereas at a sample rate of 500 kilo samples per second, it is difficult to determine uh, the exact propagation delay. So that is one particular test which cannot be performed. When it comes to functionality test would go hand in hand with the VOH and VOL test. So it would be a simple code, a single code for it. This is the typical pinout which can be observed through the data sheet, and this is the functional diagram wherein the A naught and B naught will give a result of S naught, A1 and B1 will give S1, and so on and so forth. This is the carry in bit which will give the input bit, and this is the C out or the output bit. When it comes to connecting all the pins, all the 16 pins which are present on the IC, the overall connection will look really cumbersome, wherein there would be a lot of wires in there. But one thing to be taken care of is that the basic benchmark is, as you can see, the left side is the MSP connector and the right side has the MXP connectors, and here is the DUT which is going to be tested. This entire area is the current generation circuit which we discussed in the previous videos, and that way one can have the entire uh, connection setup for the myRIO to operate and have particular outputs as desired. So going to the myRIO, already I made a continuity continuity code over here, wherein the code is pretty simple. We have an analog input which is coming to the sample, and there is, so I'll just delete this one. So there is an analog input which would be nothing but the measurement of voltage levels, and this particular analog input is connected to the input to the MSP connector AI0. So on the MSP connector, as you can see in the so as you can see, the AI0 stands for this particular pin in the MSP connector, which you can measure from the datasheet. So when you connect this particular pin uh, to the uh, DUT, it basically measures what is the input voltage at at that particular pin of the DUT at this particular input end of the myRIO. So in order to connect this particular pin of the myRIO, which is the AI0 pin, you have to connect the AI0 minus the analog ground and this analog ground, which would be this three pins would be tied together to ground level. So that is something to be taken care of. And once that connection is done, as per the continuity test, the as per the continuity test, the uh, the ground side, which is towards the left of this particular screen in this particular video. So the left side is the ground side and the right side is the ground side is the VCC side. So my ground pin, my as per the continuity test, my VCC would be grounded. So this is the VCC. It would be grounded, and this is the ground pin on my IC, because the notch is over here. So if you see the data sheet and the pin configuration, the VCC would be here and the ground would be here. I will recommend it everyone to keep the datasheet at hand while referring to this video while performing this test, because it would be a good convenience. It would be a good convention to follow in order to understand what kind of uh, what kind of pin configuration is there on the integrated circuit. And in order to make a continuity test, this particular VCC needs to be grounded, and typically there would be an input current which would be coming from this portion of the circuit, and it would go to the pin under test. So there are, except for the ground pin and the VCC pin, there are 14 other pins which can be tested for continuity. and a typical continuity test pin would be I would uh, I would ground the VCC pin over here and give an input current. So this particular continuity test is based on previous continuity test video. So I would recommend everyone to refer to those videos and follow the exact procedures which are there in the previous video. However, I'm just giving you one particular example how to perform a continuity on this current IC. The other things would be left as homework. So I'll save everything. Uh, Diode voltage drop which is obtained is point minus 0.63439, which is around 0.64, which is fairly acceptable within the range uh, for the ESD potential drop, and this shows that the continuity test is successfully performed. Now moving on to the next test, which is the functionality test. So I have a code which is made previously for the functionality test. You can easily try it out. It is simply following the steps for the as shown in the previous video for VOH VLAN functionality. However, in this case, as I have shown in the presentation, there are several connections. There are several connections to the DUT, as can be seen over here, which are connected to the MSP and MXP connectors. Uh, the corresponding VIs for all the connectors are as shown over here. So in order to understand what kind of VIs are correspond to a particular connector, we can see from this particular pin configuration, wherein the S1, S0, S2 and S3 are the respective sums, and which would be carry forwarded. So which would be carry forwarded in every step. C in and C out. So if I click this, it would be a high, and if I don't click it, it would be a low. So if I run this particular code, I can see that initially everything is off because there is no VCC given. The VCC which I'll give would be with respect to the data sheet. So if I give 2 volts as per the data sheet, the VCC value is 2, what going to look at as 2 volt, 4.5 volt for VOH and VOL. So as I can see that S0 is arbitrarily on, and it is going to be consistently on throughout. However, let me check whether the carry forward logic successfully works in in this case. So if I give a C in, the carry forward takes place because this particular entire state is high, and giving an additional high switches it to another level on another bit. If I give a high over here, the initial high at S1 and the high at A1 will lead to a transition on the third bit, which is S2. If I give a high here, that particular high logic at S2 is then is transiting on S3, and if I give the final high here, we can see that the C out goes to high, wherein I can just keep this off. Well, keeping it off will give this particular logic high because this is high. However, the main point throughout the experiment is that S0 is everything depends on the particular truth table over here, which is this is the truth table. So as I mentioned earlier, the typical S0 level is going to be high all the time, and if we compare this particular truth table and try to emulate this particular truth table on the code which we have developed for a VCC of 2 volts, we can see that the values A1 to A4 over here are nothing but A0 to A3 in the pin layout here. Similarly for B0 to B3, and this is S0 to S3. So as per the first line, all the A's are 0 except for A3. So let me put A3 as high. Wherein let me put A3 as high, and let me put B1 as high. So my B1 is high, and then my carry out bit is 0, which is eventually 0. My S1 so my S0, S1, S2 and S3. So S1 and S3 are high. So my S1 and S3 are high, whereas by default S0 is going to be high because that is how the connection is, internal connection is on this particular IC. So except for this particular point S0, all the other logics are satisfied as per the truth table. Now let's move on to the second one. Here as it says that A3 should be high, A3 is high, B3 should be high, B3 is high. That shows that carry is high, carry is high, right? And I need to turn this off. So so all the S's are 0. So except for S1 in my case, all the other S1, S2, S3 are 0 and carry out is high, which is as per the logic. Except for this particular S0, all the other logic levels are satisfied. Now let's try for the third one, wherein it says that A1 is high. So my A1 is high. Then my B3 is high. So my B3 is high. So my A3 is low. It shows that my carry is 0. So my carry is 0. S3 is high, which is as it is shown, and my S1 is high, which is as it shows. S0 as usual by default it is high. So you can try for the other logic levels as well, which clearly shows that this IC follows the truth table for a 4-bit adder, and hence its functionality is successfully tested. When it comes to VOH and VOL levels, VOL levels are something over here 0.006, 0.006, and then VOH levels are 2.02, 2.02, 2.01. As I had mentioned in the in the slides, the resolution for NImyRIO is plus or minus 50 volts and plus or minus 200 volts. So there is certainly going to be some kind of a resolution error in getting the actual values, and hence we are observing such a kind of deviation from the VOH and VOL values as per the datasheet, which is as over here. So 1.9, which is what we are getting at 2 volts, and VOL we are getting at 0.006, and here it is 0.01, 0.1. So there is a deviation, a significant deviation when it comes to VOL values, but VOH values, it is pretty close enough, but the resolution causes a serious problems at low voltage levels. Let's try for a different VCC level. So let's try for 4.5. Again, we see that 4.5 is the VOH and 0.004 is the VOL, which is again what we observed because of the resolution errors in the NImyRIO. However, the truth table remains the same, so the logic states haven't changed, which proves that the functionality is true for this particular IC. Uh, let's give it a try for 6 volts and see what happens. So for 6 volts, as I can see, it can go up to 4.99. Primary reason is the analog limit of analog limit of 5 volts, and that particular reason leads to a limitation over here at 5 volts, and hence we can't see any particular value going beyond 5 volts. However, the VOH level is 5.9 volts, and certainly it won't meet that particular levels. So to conclude one thing, whenever you're doing a test for a particular 4-bit adder, keep the truth table in front of you so that you can appreciate what kind of logic transitions are taking place. That way you can understand functionality. Certainly, the portable instrument has its own constraints and limitations, because of which all the results are not accurate, but it can be an approximate understanding of what is the logic level and voltage level that you reach to. And third thing is, definitely there are certain tests which one would like to do, but the sampling rate is very poor on the portable instrument, because of which it is not possible to do all the experiments there and there, like the propagation delay. However, it is a good ballpark estimation of what kind of functionality you can see on a 4-bit adder using a portable instrument, and definitely one can perform continuity test using this particular portable instrument. Uh, One suggestion would be to follow the previous videos before performing this particular video on the 4-bit adder, because the basics of making entire connections are very well explained in the previous videos. So thank you for your attention. Perform the experiments. Good luck with them. Thank you.